All right. So this is the decay equation, and you can understand. We considered before at a given time 100 nuclides were there as parents and 20 decayed, and now we have 80, and 20 daughters should be there, right? So by the mass spectrometer, we can measure whatever the number of parent or daughter nuclides available in the present day sample, right? So that means we can find we can find out some of these parameters. That means we know n. No, sorry, we don't know n. Right? Sorry, we don't know n because this is the original amount. We don't know that, right? But we know d because we can measure, right? And yeah, and we can find out the present day parent also. So we have a present day parent uh, amount, number of nuclides, and we have present day uh, daughter nuclides, and we know the decay constant as well. We know the decay constant as well. And what is unknown is this n and the original ratios, n and t, right? So there are two unknowns there. So for that, we have to find two equations, but actually there are no two equations. We are not using two equations, but instead we make this equation in a form of a straight line, right? Remember, I showed it last time, right? So we can convert this equation into in the form of a straight line. So then what you do is you have the daughter and you have the parent, for example, because these are known variables, and you, because we get them from the mass spectrometer. Okay, so we plot them and make it a straight line. With that straight line, we will get an intercept, right? We'll get an intercept. That intercept will give you the initial amounts. Okay, and this slope, it will be directly correspondent with this uh, this component e lambda t minus 1. So from that you can directly find out t, because if you know, or you can measure this slope, right? You can calculate that, and with that you can find out the t, and also you can find out the initial amounts, also initial ratios, right? This is what we are doing in isotope geology. Okay, we just started the rubidium strontium system last week, and I just introduced you the rubidium strontium H equation based on this original or preliminary equation, right? So as we know, rubidium 87 decays to strontium 87 plus a beta particle is emitted. Okay, so this is the equation, chemical equation, chemical fractionation. This is what is happening there, and the lambda has been calculated uh, uh, by experimental methods as this number. Okay, so you are given the lambda, the decay constant. Uh, one important thing regarding the periodic table that we were talking about some time ago, right? We have compatible and incompatible elements in the periodic table. Compatible elements means those who prefer the solid phases, and incompatible elements means those who prefer the liquid phases. So minerals being solids always try to get attracted compatible elements. So in the case of rubidium also potassium, uh, they are more or less uh, uh, preferred to be partitioned into micas and alkali feldspars in most of the rocks. So these are the most available potassium and rubidium bearing minerals in rock systems, right? So potassium feldspar will get definitely potassium. Micas will definitely get both potassium and rubidium. Okay, so we consider micas are a good host for uh, this type of rubidium and potassium. These are alkaline elements. These are alkaline elements, and they like a lot of uh, fluid bearing phases. That means mica is a hydrous mineral, so there is a high chance for these elements to be concentrated in mica. So if you want to do rubidium and strontium dating, it's suggested that you you collect these micas, you separate the minerals, that means mineral separation, and do rubidium strontium isotopes. Or otherwise, you can make the whole rock into powder and do this rubidium strontium system. And in the case of strontium, which is the daughter product, right, it behaves like calcium, right? So that means it likes to be in plagioclase and apatite, right? They are calcium bearing phases. So instead of calcium, strontium can be replaced there. Okay, it's a kind of ionic replacement there uh, in plagioclase and apatite. So they are very compatible uh, with plagioclase and apatite, strontium, right? But remember, clinopyroxene can take some strontium, of course, because calcium is there in clinopyroxene, but not as much as plagioclase or apatite. Okay, but still it's possible. The reason is their crystalline structures are different, right? The CPX crystal does not there are what you call uh, sites, yeah, site assignments, right? There are different sites in crystals, right? These M site, T site, M1 site, like that. Some of these sites will not, I mean, depending on its shape, uh, the amount that can accommodate is different. That's the general meaning. Okay, so in plagioclase and apatite, a lot of strontium can be stored, but not in clinopyroxene. They can store, but not much. Okay, uh, so if you take the relative ratios, relative amounts of abundances, 88, 87, 86, and 84, these are the isotopes available for strontium, right? If you have a strontium element mixture, definitely there will be uh, different types of isotopes like this. Okay, so usually they are in the proportion like this. So you can see the 88 is the highest. 88 is the highest, and 86 being a stable isotope. It's not a radiogenic product, remember, right? It's a stable product because we are going to use that to make the ratio with this parent and daughter, right? So 87 rubidium divided by 86 strontium, and 87 strontium divided by 86 strontium, like that, right? Because for get a more precise value, rather than getting numbers of molecules or nuclides, it's suggested to have ratios, because they reduce the uncertainty, they reduce the error when you take ratios rather than pure numbers. Okay, that's why in isotope geology we always normalize it into a stable isotope, right? We take it as a normalized ratio, as a uh, ratio. That's the reason. So 86 is a stable isotope. That's why we take it, and it's not created by any breakdown of other parent atoms, right? Nothing. Strontium is independent, so it doesn't change with time. So that is a good parameter for the denominator. Okay, so we talked about uh, a, a line, right? Remember previously we told that we measure the ratios parent and daughter and plot them, and they behave more or less like uh, in a straight line, right, according to the equation, right? So this straight line actually is called the isochron, right? This is called isochron when you use several uh, minerals or several rock samples, I mean multiple samples of the same rock, or uh, multiple mineral fractions. So if you measure the parent daughter isotopes in different minerals in a same rock, for example, you can measure amphibole, clinopyroxene, what else? What is the strontium? Uh, yeah, plagioclase, apatite, micas, like these minerals. If you separate them out and you separately measure their isotopic ratios and plot, right? So then, if you plot them, if they are originating from a single source, that means if those minerals or if that rock has behaved in a closed system, right? If nothing has came out from the external system, or nothing has gone out from the system, that means the rock itself has remained as a closed system object for the given period of time. That means at least for this time t that we are going to measure, right? We are going to calculate. At least for that time period, if nothing has exchanged in between, okay? Uh, these minerals, the measured minerals, should give you an approximate straight line, right? You will never get a perfect straight line, but there will be an approximate straight line. That means some points might be deviated from the straight line, but you can make a good uh, straight line, right? So this straight line is called an isochron, right? This is called an isochron uh, uh, because for making an isochron, there should be one original isotope ratio. So that's why we wanted this particular rock to be in a closed system. Okay. So if it is originating from one single original isotope ratio or parent isotope ratio, right? All these minerals will be formed from that. That means at the t time that where when that rock started to crystallize, everything will have the same parent isotope ratios because they are originating from one single magma. For example, if magma crystallizes one rock, say rhyolite or basalt, okay, because the parent magma has a given isotope ratio, given parent daughter isotope ratio at that time, okay, that ratio will be incorporated into all the minerals originating from that rock. So that means they must have same original ratio. So if nothing happened, if now let's say today is here, okay, let's say T1 today. If nothing happened, right? That means if there is nothing called radiogenic decay, right? If nothing happens like stable isotopes, if everything stays there as it is, what should be the behavior? It must have evolved like this, right? Nothing will change their original isotope ratios. Okay, nothing will change. But uh, with time, we know radiogenic isotopes decay. Okay, so with time they decay means at a given at a certain period of time, say after 50 million years of t time, right? So initial time is original time, or the crystallization time is t. So after 50 million years from that time, say you just put here 50. If you put just 50 here, uh, what will be the values of these uh, decay system, right? Ideally, uh, they may have some evolved values, evolved ratios. Definitely, they are producing new decay, new isotope ratios, so that they will behave something like this way, right? From time to time, uh, the original from the original value, they must have evolved into a value like this. But those all those values, evolving values, should be correspondent to a one single line. That is the reason for the straight line behavior you are getting from that particular equation, right? If you are getting some values, for example, say beyond this uh, straight line behavior, that means if you are getting some value, present day value somewhere here, present day O at a given time, right, at this time, some value here, that means this particular sample has not been part of your system from the beginning, okay? Or otherwise, your system has affected by an external process, right? Either something has gained or something has lost from the system. So that means it depends on whether it's lying outside the straight line, maybe here or something like that. So whatever the points that you have in this line aligned will be consistent with the straight line. That means they were part of the original system, right? So if you are getting a value outside that, that means you are considering something exterior, right? So that means the original or the closed system behavior cannot be expected for your system. Suppose you are analyzing multiple samples of a single rock, right? Whole rock, a multiple sample. In that case, in that case, what you can expect? Maybe you are getting a very nice linear plot like this, or otherwise you might be getting some very scattered type of a plot. Okay, so in that case, we have to think that this situation, this scattered situation, has has been affected by secondary processes, later processes. Okay, later processes, not secondary, later processes. You can use the term secondary also, but it's okay, right? Because we don't know at what time this happened. Okay, so but if you are getting a very nice equation like this, then your assumption is uh, correct, right? For the system to be in closed system. Okay, so we will come to some examples later on to explain this thing further. Uh, so actually we need at least three samples, right? At least three samples, because to draw a straight line correctly, you need at least 3 points, right? You can draw a straight line with 2 points. That's no problem. But how do you know this is correct? If you were supposed to have three compositions like that, right? You can draw uh, multiple lines like this, right? But to make a very precise straight line, right, if you have 3 points, that will be good, right? That's why we need at least three samples, or three samples to make a good isochrone, right? To make a good isochrone, at least you need three samples. Otherwise you don't know whether this isochrone is heading like this, or even it can go like that if you had the third sample giving a ratio like this, right? So that will be a problem then, right? But if the third line also, third point sample also gives you a value very close to this line, then no problem, this line is correct. Okay, so that's why. So the other thing is, it's very important that you get a co-genetic sample. What do you mean by co-genetic sample? Okay, again the same problem. Right. So you need three co-genetic samples. Okay. That means they should have been derived from the same source. That is the meaning. Co-genetic. Okay. Uh, So if uh, because you have in a one rock, right? You take one rock, and one rock contain lot of minerals, right? Suppose you have three minerals which compose this compose this rock, right? You can say mica, plagioclase, and hornblende, right? Just mica, plagioclase, and CPX, let's say, right? So you have CPX, mica, and plagioclase. So original rock contains some amount of rubidium, okay, some amount of rubidium, and some amount of strontium also, because at that time we don't know at the time of crystallization, right? At that time there should be some strontium also, right? As the initial amount. Uh, so if we take these three minerals separated from the rock, that means you can crush the sample. Can you hear me? Is it clear? Oh, dragging the voice. Is it clear or dragging the voice?
Yes.
Okay. So you have three minerals, but we consider this rock derived from a single source. But in this case, in this particular example, we consider three rocks derived from one source, right? But in this first example that I am going to tell you now is exactly one source for three minerals. Okay, one source for three minerals in this case. But in this situation, you can have three rocks derived from a single source. That means one magma, sorry, one magma can give rise to three rocks, right? Three crystallization, three types of rocks. That is also possible at a three stages. They can produce three rocks, because you can have the magma branched, right? Uh, if you have one magma conduit, it can branch out, right, in the system. But later on, due to tectonic processes, all these rocks might be associated in one region at the present day scenario, right? Like if you go to the Randanigala road, you see a lot of layers in one locality, but different compositions, right? So similar type of a situation. If all these rocks have derived from a single source, then you can take those samples for your isochron work. Otherwise, you take a separate rock and do mineral separation. Then you take separate minerals of that particular rock. So these are the two situations that we deal with in isochron techniques. That means if you are very sure and if you are certain that this must be the same rock coming from one source, that means you have to study it before going to isotopes. That's why we need to study petrography and petrology before going into the isotopic determinations. So based on those evidence, if you are certain that three rocks coming from the same source, then you can straight away take them and measure and do an isochron plotting. Otherwise, you have to take the samples separately, the three samples separately, and do mineral separation, right? So, within one single rock, the mineral should have been crystallized from one source. That's the thing, right? So in that case, you will get an age for one rock separately, and another age for the second rock, and the third for the third rock. So if you, still you might get the same ages if they are cogenetic. So this is the importance of the cogenetic samples you have to consider for isotope dating. Otherwise, your isochron or your straight line will not be correct. Okay, so because we have based on this large, this big assumption that they are deriving from one source, a single source, or cogenetic. The samples are cogenetic, and they have not exchanged anything in between, right, from the system. So like that. So anyway, so you can have this isotope ratios calculated and plotted uh, in uh, a diagram to find out the date or the age of that particular rock. Here, what I want to show you is another thing, that is CL over CO. What is CL over CO here? This is actually the element, right? You can take any element and find out its composition when you make that rock, right? So, okay, you have a magma here. Okay, I'll put it in a different color. So you have a magma here, okay, and this magma makes this rock. Okay, this magma makes this rock, right? So when you make this rock means you may you have to, I mean, the magma has to partition different elements. I taught this lesson in advanced igneous petrology, okay, already. So the element I which want to incorporate into this rock, this is a solid, right? The magma is a liquid. So this is crystallization process. Okay. So when this magma crystallizes this solid, this rock, right? Or accumulate or collection of minerals, that means it's a rock, right? Magma crystallizes rocks. That means magma crystallizes minerals. Okay. So you have two phases, right? You have two phases because this is within one single magma chamber, and the more uh, solid loving elements, that means more compatible elements, right? You remember the term compatibility and incompatibility, compatible elements and incompatible elements. Just a while ago, I in a previous slide I explained the elements which likes solid phases are compatible elements. Elements like liquid phases are incompatible elements. For example, we took the example of clinopyroxene, right? And compared it with plagioclase for strontium, right? We told strontium is more compatible in plagioclase than clinopyroxene because we said uh, plagioclase can contain a lot of strontium, but cyanopyroxene also contain some strontium, but not that much of I mean, not as equal as the plagioclase can do. Okay, so that is the compatibility. So anyway, the minerals which like solid phase, I mean elements which like solid phases will go more into the crystallizing phases. So that means uh, the rubidium and strontium, right? In the case of rubidium and strontium, if you are crystallizing uh, plagioclase and clinopyroxene, there will be a lot of rubidium going into the lot of strontium will go into the uh, plagioclase than CPX. So likewise, the original or the initial amount of strontium and rubidium available in the system will be divided. They will be divided into different minerals, right? They will be divided into different minerals depending on their compatibility and incompatibility. In the case of rubidium and strontium, the rubidium is also same. The elemental rubidium that can also, for example, if for mica, it can has a high affinity. That means if you are crystallizing mica also here, there will be a lot of rubidium going into mica rather than other minerals. So that means the initial amount of rubidium and strontium available in the system will be divided. Okay, rubidium and strontium available in the system, initial number of nuclides will be divided because of this fractionation. We call this elemental fractionation. Okay, not isotopic. Here, this is elemental fractionation, right? I taught this at the igneous petrology when we take the partial melting. So partial melting or fractional crystallization, whatever, can uh, have the same effect, right? So anyway, you just think that these elements, these parents and daughters also, available daughters at that time, will be distributed differently between the among the among the minerals crystallizing there. So even though you had an initial rubidium and strontium ratio as such at that time, when these minerals crystallize, they will modify this initial ratio. That means for mica, at the time of crystallization, may say 20 rubidium came and 15 strontium was there, and for plagioclase, uh, just 15 rubidium, 12 rubidium came and say 10 strontium came. So likewise, the number of amounts of nuclides coming there is different. So that means at the initial time, this fractionation happens, right? So that is the that is the situation uh, happening in a rock system. So this is a little bit complicated situation, but you have to admit that elemental fractionation happens at the original situation also, right? So with examples we will understand that, right? I think you will get that clear initially. So F means here different degree of melting, right? Different degree of melting if you consider the partial melting, or otherwise different degree of crystallization if you take the fractional crystallization. That means the whole melt might not crystallize a large amount of solids, okay? Or otherwise, if it is melting, the the solid residue, the solid material go which goes on melting will not produce a large number of liquid at that time, right? It all depends on F. F may be 1%, 2%, 3%, 10%, 20%, like that, right? So with that, you will see how rubidium can be incorporated into the solid phase or into the liquid phase. Okay, so rubidium being the parent isotope, there will be all radiogenic nuclides accompanying there, so that they will be changing due to incompatibility like this. It's also an exponential type of variation. These are experimentally determined. Okay, the strontium, but being very compatible in the compared to rubidium in the solid, it might not change much, right? Although they separate out like here, right? Although we consider that they separate out, but there will be no big change. So that's why throughout the amount of melting changing here, right? Changing the fraction amount of fractionation amount of melting portion, the degree of melting, strontium doesn't change considerably, but rubidium changes much. So that means the take-home message from this diagram is that rubidium can take, rubidium is very sensitive during this melting processes, melting and crystallization processes. Okay, so we will take some examples later on so that you can understand this behavior. Okay, so right. If you haven't noted this down, so please just note this down. And also, we have to take a note of this graph. Can you just draw this on before we explain it? It will make it easier for you to understand. Just sketch this down, this graph. Okay, right. So just recall the age equation which can be applied for the rubidium strontium system. Do you remember the last slide that I taught you last week? We have this equation, right? This strontium 87 uh, to 86 strontium, the present day value. This is the present day value, and initial value is this one, and the amount decayed, I mean amount produced as the, from the radiogenic decay, right? This is coming from the decay equation, right? Do you remember that? The original decay equation, okay? Uh, Here, it is coming from here. This is the radiogenic amount coming out, okay? Right, radiogenic amount coming out is this much, okay? This is the radiogenic amount coming out after elapsing T period of time, okay? After elapsing T period of time, this is it, all right? This is the parent, this is the parent which produces strontium, 87 strontium. So this is the daughter, produced daughter, right? So this is the total daughter nuclide amount in present day situation after elapsing T time period of time. So you have present day value, let's say P, let's say present day value is P, will be the present day what we measure as the radiogenic product, say this is R plus its initial amount, because it has already got some daughter isotope at that time, right? At the time of the T time before, right? So that amount will also be there in your uh, calculation. I mean, from the mass spectrometry, what you get is today, whatever the number you can count today, but it doesn't mean everything counts for the radiogenic decay, right? One part will be the radiogenic decay, and the other part should be the initial amount, right? So initial amount plus the produced amount during the radiogenic decay. So that's why this equation comes like that. This why this strontium comes 86 here. I think I explained it. You need to make all ratios, right? You have to normalize it. The reason is, rather than counting nuclides 1, 2, 3, 4 like that, and the produced parents, produced daughter, and available parent nuclides like that, there will be large errors occurring, right? If you make it 60 parent and 75 daughters like that, and if you make a mistake in due to some reason within the system, right, the error will be large, right? Uncertainty will be very large, right? But instead, if you take some ratios, in that case this error will be also diluted, right? Because you have a numerator and denominator, so since both contain some errors, the cumulative error will be small. That's why we take like that, right? Because we know the stabilized dot will not change at all, so that's why we take it as a denominator for normalizing. If you take a radiogenic isotope as a denominator also, then it is a problem, because that is also getting changed with time, right? So that cannot be precise. Okay, right. So this is the equation, and this is what we are going to apply in this case. So as you can clearly see, this should be giving us a straight line, because this is in the form of y equals mx plus c form. Okay, so this is y here, and x is the other parameter, that is this one, rubidium, and m is the gradient. It should be represented by this term, and c, that is the intercept, should be this one. Okay, so for the x and y uh, variables, you can put here x, that is rubidium strontium, and y is strontium here. So this is y equals mx plus c type equation. Okay. So at the beginning, right, we are beginning with three rocks, right? Beginning with three rocks means, suppose you have to assume that this is coming from a cogenetic suit. That means all these rocks are coming from one single source, right? That means the initial ratio of this strontium must be constant, must be same for all the three rocks, A, B, and C, right? At the initial time, that is T naught here, as shown here, right? All the rocks should show the same initial ratio. So that's why they are lying in the same level, A, B, C. Three points are there. Okay. So we'll see with time what happens. So this rock, okay, but okay. The daughter products will have the initial ratio, but for rubidium, you don't have the same ratios. Why? Do you understand that? This is the important concept. We just explained it in before slide here. The distribution is different. See, uh, depending on the compatibility and incompatibility, the rubidium goes uh, in different amounts. All right, rubidium goes in different amounts during the formation of the rock, right? The strontium ratio which is available here is the ratio that was available from the parent. Okay, that is a, because we are considering this as the daughter. This is the daughter isotope. So we take that ratio, and which is in constant amount because they are coming from the same parent. But now we have crystallized the mineral, crystallized the rock, but during the crystallization process, this rubidium enters into different amounts. So therefore, you will have different amounts of rubidium ratios, rubidium amounts in your rock. Okay, but you understand the initial strontium ratio should be constant for the given rock, because this is the daughter product that we are not considering anything uh, as a radiogenic decay product. We just forget about the decay, but we just only consider the initial amount present there in the rock, right? So that is this amount. This is the constant amount. But for the rock 1, 2, and 3, depending on their model percentages of minerals, because although these three rocks are derived from one single parent, they will have different amounts of minerals in model percentages, right? There can be different because they don't need exactly to be the same, right? Because they are three rocks. So amounts of rubidium entering during the crystallization process, right? During the crystallization process is different, but this ratio is not, not the changed strontium during the crystallization process. We take the initial amount of strontium available there. Okay, if you, of course, strontium will also be changing in these three rocks like rubidium, but we are not bothered about that. We take only the daughter amount which was available at the time of crystallization in the source. Remember, this is in the source. The source for the rock 1 is the same. The source for the rock 2 is also same. Source for the rock 3 is also same. So for the source, initial composition, initial value that you are getting here is same. That's why we have a constant value here. But once the new rock crystallized, you will have different amounts of rubidium distributed coming out from this source in different amounts. So that's why you have different rubidium strontium rubidium ratios, uh, and when you normalize it also, you will have three different values for the three rocks. Okay, so always remember, we take the original source initial ratio, right? Original source initial ratio, which is constant because the source for these three rocks are same. It's like you have three children from the parent, right? So the parent is same, but the three children will have different properties. Okay, original DNA signature will be there in all the three people, although they have different uh, characteristics depending on their evolution. So that's the point. The original signature must be there as a constant there value. Okay, so now you have these three rocks. Otherwise, all the three rocks will should plot here, isn't it? At one place, wherever, right? So no, it doesn't happen because the fractionation amounts of different minerals are variable there, right? There can be plagioclase 10%, the other one may be plagioclase 20% or something like that, right? So it depends how it fractionates. Okay, but the point is you should have clear in your mind that the original source, the source region or the source material should be same for the three suits that we are uh, discussing for the age determination. If you are uncertain about this the source, then we can go for the second option. What is the second option? From you take just one rock, you take just one rock and you separate minerals, you separate out minerals. You can separate cpx, you can separate uh, plagioclase, you can separate what micas, like that. And you measure, you try to measure those things. Since all these minerals were also crystallized from one source, because this is a single rock that you are talking about, their initial strontium signature should also be same, right? So we can take the strontium as a constant value, but rubidium will be changing because you have plagioclase here, you have cpx here. The amount of rubidium going into plagioclase is different than amount of rubidium going into cpx, like that, right? So therefore you will still have different 3 points for your minerals also if you are taking just a single rock, right? So you can forget other rocks and you can go for a single rock by mineral separate. Actually, this is more precise than taking this type of three rocks as assuming they are cogenetic, because in a single rock you are very certain that these minerals are coming from the original source, right? That's why people like much for mineral isochrons. So in that case, if you plot these three minerals in your strontium rubidium plot, you call it mineral isochron. Okay, rubidium strontium mineral isochron. Uh, but in this case, we are plotting three rocks, assuming that they are coming from one single source. So if we plot this one and get an isochron, uh, we call it whole rock isochron, right? We call it whole rock isochron because we take each rock as a whole, right? We take all, I mean, a representative sample and we crush it together, not separating minerals, as whole rocks, right? So in that case, we produce a whole rock isochron. But if you separate minerals and make an isochron, then it's a mineral isochron, right? There are two types of isochrons also, right? So if given t period of time, so let's see what has happened. Originally, we had these 3 points for these rocks, and initial isotopic composition was this much, right? So at a given time of t, right, it takes t period of time uh, to make it from t0 to t1. Okay, the elapsed time is t. Elapsed time is t. Say for our rocks, if you did this, it must be like at least 550 million years. T should be equal to 550 million years at least, right? So during this t time period, your rubidium strontium decay will produce a new ratio, right? A new ratio, that is what you are measuring today, actually, right? Because you don't know initial ratio at least at the time of beginning. So these are the ratios produced and measured today. So from rock B, after T period of time, you must have a ratio of say B1. And for rock C, you must have a ratio of C1. Always remember these are the present day measured value, right? Present day measured value of strontium and rubidium isotopes. Okay, so you go back to the equation here. What do you measure by the mass spectrometer? What do you measure by the mass spectrometer? You measure this daughter isotope ratio, which is available today, because we are measuring the today's sample, and you are measuring the other ratio, this one, from the mass spectrometer, uh, rubidium strontium ratio today. All right. So these are the two things we measure today. That's why we have XY graph, right? We can make XY graph. That's the reason is we are measuring these two values, and we try to plot these numbers. That is what you see here by this line, right? Do you actually see this line? No, we don't see this one beforehand. We don't know, right? Because we don't know initial value. But now we are just assuming we are going to demonstrate this principle. That's why we assume some value as the initial ratio and take it up. Otherwise, from the mass spectrometer, we are getting only the present day values. So the present day values means, say the T1 equals today, right? Present day. All right. If this is today, we are getting these C1, B1, A1 values, because we get rubidium ratio and we get strontium 87 ratio, right? That we get plot. Actually, what you can plot and what you can see after your ICP-MS analysis is something like this. Just three values like that, right? This line you can't see until you make this particular line generated. You get these 3 points and you generate this line and you extend it up to the y-axis and you find this ratio, the value, and then only you can determine this level or this line. All right, by the intercept of this one. Okay, but we are demonstrating what is happening during this age determination. So originally we had should have we ideally we should have A, B, and C values for these rocks A and B, A, B, C. Initially, since they are coming from the core genetics, so they must be in the same level, right? That is what we are later uh, arriving at, right? Okay, so original composition is this one, right? So after t time elapse, this rock A will evolve like this. This will evolve like this. This will evolve like this, and this will evolve like this. That is the that is what is happening. Why this happens? Do you understand that? I think it's very easy, right? You take the rubidium and strontium, two axes. What happens? This is the parent. Okay, this is the parent. So you have A here, right? You have plotted A, say at the original time in this case. So I'm just explaining you this behavior. You have rubidium some number here and strontium some number here. Okay, you have rubidium some number here and strontium some number here. So what is happening during this radiogenic decay? Rubidium should decay to produce strontium. That's all what is happening. Rubidium decays to form strontium. That means number of rubidium atoms will be getting, nuclides will be getting decreased, isn't it? Okay. Initially, some amount of strontium was there, but now what is happening is, as a result of this rubidium strontium decay, strontium nuclides will be increasing. The number of strontium nuclides will be increasing. So what should be your result of this equation? I mean, in the plot behavior, your rubidium will be decreasing like that, your strontium will be increasing like that. So what is the overall shape of this change? It should be evolution like that. So that's why you have a evolution like this in this plot. Okay. That's why you are getting some evolution like that. This one by one evolution. Okay, for A, for B, and for C. Rubidium decreasing, strontium increasing. That's why it is going in a leftward type of a evolution, right? Inverse type of a evolution, right? So now today you get from rock A, you get A1, the ratio A1 of strontium and rubidium value. Then you plot here, and then from the rock 2 you get that value, and rock 3 you get that value, right? Uh, since we these the three rocks are coming from the one source, one single source, ideally they should be behaving along a straight line, right? So this is the isochron or the straight line produced at present day. Okay, at the time t1, that means today, after elapsing of t number of years. Okay, after elapsing of t number of years, we are getting an isochron like this. All right. Okay. Anybody didn't understand this? I can explain from the beginning again if someone needs. Always remember, don't get confused that this is the original protolith isotope ratio, right? Protolith daughter isotope ratio. Initial ratio means protolith isotope ratio. Okay, right. So this is the concept of uh, isochron. So after time t, what you get here will be along a straight line again, right? At the initial time also they should be along a straight line, just simply because they had a constant ratio. That means they are coming from one single source, right? So always remember rubidium loss, right? Rubidium loses some number of nuclides equivalent to the amount of its daughter produced. That is the concept behind this. Okay, number of rubidium nuclides loss is equal to number of strontium nuclides gained. Okay, those two should be same. That is how we derived at the age equation, right? At the initial steps during this uh, integration and differentiation. So you refer the book of Gontafor or Alan Dickens in the science library, and you can easily find out how this age equation is derived. And they have clearly explained about this phenomena as well. So you must read that and get your knowledge refreshed. Okay, don't forget that, and don't complain me after the exam that you don't it was very difficult or something like that, right? It's not difficult as long as you absorb the concept. Okay, so we will go to another step. That means we just considered only one step. So we considered this one step as the present day. So we will take present day is not yet, right? So maybe it started at 550 million years ago, and we just now considered at the situation of 300 million years ago, and now we are going to extend it to the present day. Let's say we had a uh, third stage, right? I mean, like this, you can have multiple number of steps, because at each and every time period, there will be a isochron, right? What we are interested for age dating is today's isochron, right? Because that will give you how long it has elapsed from the beginning, right? So there can be multiple isochrons. So this is the isochron at say 300 million years ago. So this is the situation at 300 million years ago. But the next step, we can extend it to the present day. Then it will be the today's isochron. That means the age corresponding to today. From today, how many years? Here you get how many years it has elapsed from 300 million years, right? That means this time period. So you can add the next time period also and find out the total time. Actually, you don't need these intermediate isochrons. We can directly have it as we explained here, right? So you can just have the present day values, but just for explanation of this process, we can take several isochrons at several different time frames and explain the behavior of this rubidium and strontium system. That is what is given here. So originally at the t naught time, it's like repeating, right? So if those who did not understand, you can understand, you can get it absorbed here also, right? So after t1 time, maybe you are getting an isochron, so you get the age of this this time interval, right? And you have another isochron after some time, after elapsing more time, so then you get t2, right? You can draw another one at time interval t3 if you were to do that. Then you can get that time, and like that we can measure the present day values and get the today's ratios and age for this whole t. Actually, these interim isochrons we cannot do because these were corresponding to the past, right? 300 million years ago, maybe 400 million years ago, like that, right? But we can't. Actually, there is a way for doing that. We call age correction. There is a process called age correction, right? That means we determine the present day isochron, right? Present day isochron here, like we did before, and we backdate it. There is a process called age correction, and you can find out the isochron at some time ago, right? So likewise, you can produce all these intermediate steps. Okay, you can produce all these intermediate steps by this age correction technique, right? That you are not going to do here at undergraduate level. If you are going to do some postgraduate work, you will have to do that, right? Because you might end up with some geological processes that has taken place in between, right? For example, I will take one example. If you have some rocks analyzed, and you find out the present day isochron like this. So if you get the present day isochron and you want to know how this isochron was about 200 million years ago, right? Present day it is like this, but you want to know, or you want to back calculate its isochron 200 years before present, right? That means something intermediate, right? Somewhere here maybe. So we can do some age correction for our present day ratios. That means we correct our ratios to the past. We put suppose we want 300 million years ago behavior, right? So you have to take the 300 million years as the age. That means you need to make this age corrected, right? Your present day ratios should be corrected to 300 million years. It should correspond to the 300 million years age. That means you have to correct it to the past, right? That is possible. And then those ratios, whatever the numbers you get, and plot here, right? You can't measure it in a mass spectrometer because you don't know how it has been there, right? So only thing is you can do a mathematical age correction only, right? Then you take those values and you can plot these isochrons, right? So likewise, there may be so many intermediate isochrons, right? With time. Okay, so always remember this the steepness of these isochrones will be different, but still they should be linear lines as long as they have remained as a closed system during this whole period of time. Okay, so in t1 time you have this isochron, and time 2 t2 you have this isochron. Like that you can have a numerous isochrons different with different steepness. Why this different steepness is because you are having different amounts of parent order nucleides. That's all, right? Different amounts will be there at different time periods, because this is time dependent. Okay, so uh, the the essence of this technique is you are getting two valuable things out from this isochron technique. What? The number one is the age of the rock. You are getting the age of the rock, which is corresponding to the uh, gradient of the line, gradient of this particular line, m, which is equal to e lambda t minus 1, right? You remember that because our equation was giving that parameter. And the second one, uh, you get the original isotope ratio, the initial value of the parent, because we don't know about the parent, right? We don't know what magma derived this rock. But what we know is we have some rocks today, and using those rocks, we try to find out the original source. It's like you have children now, but parents are deserted. We don't know, right? But using the children's characteristics, we may be able to find out parents. So this is something like that. Okay. So from e lambda t minus 1, everything is known, lambda known, it's a constant, and you can measure the m, or the gradient, and that you can equal to this e lambda t minus 1, and then find out t. So this is the isotope technique that produces you these two results. Okay. Anything unclear? Do you have any questions? No? Okay. Uh, let's move to the next slide and see these two values that is produced by these two isochrons. Sorry, this isochron method, the two things, right? Initial value and the slope, that means the age, right? So this is a real example taken from the textbook. This I told you about this textbook, I think, right? No, this is a different one. Yeah. Anyway, this is a real example, right? From an igneous root in the US. So you have present day measured values, different rocks, right? Two rocks types. Let's assume two rocks because you have two symbols there. So you have multiple samples and measure them by the mass spectrometer, and you get strontium ratios and rubidium ratios, present day values, right? Today, these are the values. Okay, it explains here. filled circles are all rock analysis, but I don't know where are the open circles. Okay, okay. I think the let's say red corresponds to the whole rock. Okay, let's take this red points corresponds to the whole rock analysis, and these uh, yellow corresponds to mineral separates, right? But they haven't shown. I don't know whether separate minerals. So let's say just one mineral for the time being for the principle. That's okay, right? Okay. So if the rock is coming from the same, I mean, if we the multi, you see here multiple samples of a rock is taken. That means the same rock layer occurring in different places, like ours. You see our condylite. This is a metamorphic rock anyway, but just take it as an example. You get condylite exposed here in the university area, and you can go to Hantana and find condylite again, right? And you can go to where the Randenigala and also find some condylite there. So you collect these three locations and come here for analysis, right? So from three locations you have multiple samples, right? From one location you take several samples from one place, right? So multiple samples from one from the three main locations. That means you can come up with 20-30 samples, even whatever. The higher the number, better the precision of this isotone, right? Always remember this slope. You have to be very precise on this slope, right? That is very important, because you see here the value is E lambda t, right? E lambda t. If you make a very small change in the slope, right? Suppose your slope should be this, but you are making due to some analytical laws, your human error, an error slope like that. It's a very tiny change apparently, but I mean it will change some 0 point something in your m value, in your gradient value. But when you make it uh, uh, calculation for t, you have to take the natural logarithm of this one, right? So it will this error will be enlarged. Okay, always remember it will be going in a logarithmic term, right? So that means it will be uh, expanded more and more. So that means your t value will be deviated from the actual value to a considerable range, right? Therefore uh, the more precise slope should be used for isochrone value. That's why just by three plots or three points will not work for you for a precise age. Of course, you can make a reasonable line by regression, but it might be changing. I mean, if you put another two samples there like that, then what happens? Your line might be slightly changing. Your regression may be like that, right? Then you are changing the m. You are changing m means you are changing t. That means you are getting some other value for t. So that is very important. So therefore, if you can, better do whole rock plus mineral separate, right? It can be either one mineral, right? Like here, maybe this is just one mineral. I don't know. I haven't details given there, but it can be one mineral. But if it is multiple minerals, then much better, right? So these are the practical things that you need to consider when you are to do this isotope geochronology. Okay, so anyway, you take whole rock samples and some multiple mineral separates, and you measure them for rubidium strontium ratios and strontium to strontium ratios and plot. Finally, you will end up with a very beautiful line, very nice regression line for this set of samples, because you see all these samples are plotting very close to each other. That means you can get a very reasonable line there. And also even the mineral separates, although they are distant, right? But still they are very aligned, very well aligned with the whole rock line. So that means altogether you can get a very beautiful isochrone, right? So that will give you more and more reasonable age value for your sample. Okay, so if you have this type of plots in your paper, if you are going to publish your results, the editors will love it, right? They will immediately publish it, even with minor reviews, right? Because they understand that your data will be of high quality, right? Very good quality, right? So this is the equation. The numbers have been applied there, and you have generalized the equation with these numbers, right? This is the intercept value, 7 something, 0.7 something, and the gradient, sorry, yeah, this is the gradient, and this is the intercept. 0.00127 is the gradient, and this is the intercept, right? So once you plot this one, you get these two numbers easily, and you can put these numbers into the equation, just to show. But you can use this gradient and equalize it with this term e lambda t minus 1, and then calculate t, because lambda is known, right? You can do that. Okay. Okay. Mm, okay. Before going to this thing, I want to be very sure that you are comfortable. Are you sure there is nothing to be clarified? Don't keep things pending. If you want more elaborations, some examples, more and more examples will be there in the textbook. Okay, so please refer the textbook today itself if possible, because once you just finish the lecture, and if you have time to go to the library and see that part, it will make you very refreshed, right? Your knowledge will be very refreshed. All right. So we'll just see how this systematics, this rubidium strontium systematics can be applied to uh, in the generalized way, in a generalized way for our Earth's evolution, right? So our Earth's evolution, originally uh, s- uh, some meteoritic materials, extraterrestrial material, planetary material, which we refer as meteorite or meteorites or asteroids, right? These are the materials that contributed for this planetary formation. Should have started with a certain fixed strontium ratio, right? Initial ratio, like here, we started with an initial ratio like that. At the time of originating of the Earth or the universe, right? There must have been some initial ratio, right? At the time of planetary formation. So it's actually it is measured and known uh, something close to this value. Okay, it's very close to this value, the meteoritic value. Uh, and so from there, what happened for the Earth? The Earth started with the bulk silicate composition at the very beginning, right? There was no crust mantle core at the very beginning. I think you can well remember that. After 100 million years or so, from the initial time, that means from the initial the planetary formation step, that means the what do you call this blast, right? uh, we had just the bulk silicate earth, and then the core was separated. The core was separated after 100 million years time. So for the core, what happens, all the metallic elements like nickel, iron, concentrated there, and all the other silicate part was outside, right? It was like a magma ocean. It's called something like a magma ocean. All the silicate portion was in a liquid form, like an ocean, right? Inside a solid metallic core. For that separation, it has taken about 100 million years. Okay, 100 million years. This has been determined by tungsten isotopes. This has been determined by tungsten isotopes, right? So after that, what happens? The mantle was derived, right? Its mantle was derived, and it evolved with time. The radiogenic decay caused strontium to be produced, more strontium 87 to be produced, right? So therefore, this mantle evolution is sloping like that, increasing strontium isotope with time, right? This is time. So gradually increasing at a certain period of time, somewhere like 3 gigaannums before, right? About 3 billion years ago, right? What happened was the continental crust started to form. The continental crust started to form. Until that time, you had only the bulk silicate earth. The bulk silicate portion, it was like this, right? You have a solid core, and everything else was in a liquid form, in a magma ocean like that, right? So after about three, I mean, at a time like 3 gigaannums, 3 billion years ago, the continental crust started to form. The continental crust started to form uh, from from this bulk silicate earth. Actually, it's not total solid, total liquid anyway. It's a kind of a semi-solid material, and then it started to make partial melting, because by that this time uh, the the Earth's convection forces happening was changing, and early plate tectonics was almost starting, right? Until this time, even actually the 3 billion years of 3 billion years ago, the modern type plate tectonics was not starting. Some sort of plate tectonics has been started at that time. That means some kind of motion of plates was started because of this production of continental crust. Okay, there should be some contrast between density contrast. Otherwise, there will be no motion, right? Unless you have a density contrast, there will be no sinking or collision or whatever. Nothing will be there, right? So anyway, the continental crust started to form by partial melting of this material, this bulk silicator, and it started to form some melt which escaped outside. And this escaped out melt outside started to crystallize at the exterior, I mean at the very shallow levels of the earth. So that's why we had the crust formed, started to form there, and then you have a mantle here. Okay, now it's not the original mantle or the bulk silicate earth here. The only the top part of this mantle was contributing to this thing, right? So still the uh, deeper part, that means this area, was equal to this bulk silicate earth. So this lower part we still call the lower mantle. Okay, the upper part, that means this upper part, we call upper mantle. So the upper portion of the mantle started to partially melt and produce the continental crust. So this is how they started to separate or the differentiate of the earth, right? So then we are end up with uh, like a very thin crust, right? Like here, and we have an upper mantle, thin crust, upper mantle, and then we have a lower mantle here, and the core is here, right? So this differentiation started at about 3 billion years ago, right? So as soon as this continental crust started, it deviated from this general mantle evolution line, because now it's a new product, right? It's a new product, and the crust produced as a result of this melt, okay, this escaping melt produced the continental crust, right? So being a melt, rubidium is very incompatible. Rubidium is very incompatible. That means it prefers much melt than the solid. So as soon as this melt formed, lot of rubidium which was residing in this mantle was escaping into the melt. It's going into the melt fractionated. This is the elemental fractionation happen. So a lot of rubidium will be accumulating there, and then what happens here in this diagram, if you just put that diagram, your original, say your original mantle composition was here. Now the continental crust separated, right? So a lot of rubidium will go there. A lot of rubidium will go there means your rubidium ratio will be increasing there, and because of those rubidium, and of course some strontium will also go there, right? Strontium, because strontium is also going incompatible in an incompatible way, and strontium will also increase at the same time. Because of this increased rubidium here, they started to produce more and more strontium also, right? Not only this original strontium escaping into the crust, continental crust, more and more rubidium started to decay and produce more and more strontium. So that means uh, more and more strontium produced there, and the continental crustal, the value of this rubidium strontium ratios will be drastically increasing like this. Okay, it was increasing like that. So it naturally cause a deviation from the original mental evolution line, so that we have now end up with crustal evolution line like that, and the mental evolution line going uh, there. But because of this crustal production, the continental crustal production in the mantle, what happened, this original mantle here, the rubidium and strontium composition decreased because some of them contributed into the continental crust. So therefore, our mantle line should deplete a little bit downward, right? The continental crust will be increasing or evolving like that, and because of that loss, the mantle depletes like this in terms of rubidium and strontium. So therefore, the rubidium depleted mantle line is evolving like that until present day in this way, right? So in the depleted mantle, it's continuing this evolution like that, whereas in the continental crust, it is evolving like that, right? Assuming that nothing happened at 3 billion years ago, if nothing happened, this mantle evolution line, the original mantle evolution line, should be going as it is until present day, right? But it is not happening, but still we can extrapolate that until the today, until present day, right? So this is how the rubidium strontium evolution is taking place within the earth as a whole, right? So always remember, in the mantle, rubidium is depleted. In the continental crust, rubidium is enriched. So we call rubidium enriched continental crust, and we call rubidium depleted mantle for the counterpart. So that's why you take some rocks like granites. There are a lot of rubidium in granites, but in mantle rocks like peridotite, you will see very less amount of rubidium there. So this is the evolution of rubidium and strontium in the Earth and the planetary system. Okay. Do you have any questions up to this content? All right. So if no questions, so we will stop here for today, and make sure that you recap these things before coming to the next class. Okay. You have to read and absorb more and more, and also look for more examples in the textbooks, right? So that is very, very important. Otherwise, when you are given a problem, it will be very difficult for you to resolve it. Okay, right. So let's talk